Fractals are one of the more complex branches of mathematical study, infinitely self-similar sequences with repeating patterns whose graphs are not differentiable. Fractals typically follow this mathematical form, as they are evaluated and graphed by mapping iterations of a function using a limit statement. The most notable fractal is the Mandelbrot set, which is a horizontally symmetrical fractal with increasingly smaller circles at a set interval of 90 degrees. While fractals mainly appear in complex branches of mathematics, they are traces of fractal behavior in the natural world. Environments that endure cycles or common trends, like coastlines, for example, have fractals within the terrain due to constant erosion in some places. Trees additionally follow the pattern of fractals, with branches splitting off at equal distances all throughout the tree. Newton's method allows the fractal to be approximated by roughly discerning the roots or zeros of the equation. Using Newton's method, fractals can be visually graphed, with certain parts colored differently depending on the value returned. Given enough data, detailed visual plots of said fractals can be created using computer programs. Sophisticated code can even render up to a few million data points, allowing better access to the true infinite nature of fractals.
Alright, take 300 million and 2, starting now. Newton's method is an application of the derivative that allows you to find the roots of basically any differentiable function. It was invented by our good friend Mr. Newton here, of gravity and cool sunglasses, and the formula for it is right here. So it's a recursively defined function, kind of like sequences. So it's x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So the way it works is you take some x sub naught, which can be any function where f of x is at any point where f of x is differentiable, and plug it in here. So you would have x sub naught minus f of x sub naught over f prime of x sub naught is x sub 1, and then you can plug that back in to this, to x sub 1 minus f of x sub 1 over f prime of x sub 1, and get x sub 2, and just keep going with that over and over and over again, and then eventually you will get what will be quite a good approximation of the root. And to show how this works, let's just derive it. It's a pretty simple derivation. So we start with what will be probably familiar to you as the definition of local linearity. So we have f prime, the tangent line is for short distances the same as f of x sub 1 minus f of x sub naught over x sub 1 minus x sub naught. Now, we know that because we're trying to find a root, we know that f of x sub 1 is just 0, and so we're trying to find x sub 1. We can get rid of the approximation markings because we're just looking for the value we will find with linearity, not for the actual root, because we'll repeat it over and over again until they're basically one and the same. So we get f prime of x equals negative f of x sub naught over x sub 1 minus x sub naught, and f prime of x by x sub 1 minus x sub naught is minus f of x sub naught. We'll just keep going with algebra for some trivial steps, and eventually we get to this. X sub 1 equals x sub naught minus f of x sub naught over f prime of x sub naught. We can also write this as a function. N of x equals x minus f of x over f prime of x. And it's just how that's called the Newton function, and I think it might be useful for coming on. So here's a graphical example of why Newton's method works, because it's based on local linearity, so like having tangent lines be similar to the function. So start here, but the difference between its local linearity, of course, is that Newton's method can pick any value for x sub naught, but local linearity can only work if x sub naught and x sub 1 are close together. But Newton's method gets around this by its repeating nature. So we start with some x sub naught here, and we go down the tangent line, like with local linearity, to the point where to the 0 of the tangent line. Then we go down to where the function is already to the line, and find the tangent line there, go up here, down here, and now we're pretty close to the root. We could go over and over again. You would see we get closer and closer to the root, which is here. And that's what we're doing when we're running this local linearity over and over again. We're making it better and better and better because we're getting closer and closer and closer every single time. hopefully that's clear. So to find an example of this, we have f of x equals e to the 4 to the x plus 2x cubed. And we can start with x naught equals 0, because I wouldn't want to, we're going to try and run Newton's method on this, and I wouldn't want to just find the root of this because it seems nightmarish, but with Newton's method we'll see it's very, very easy. So we'll start x of naught equals 0, so we get 0 minus f of 0 over f prime of 0. Turns out that's negative 0.721348. Then we've gone down the tangent line like we did on the previous example. We've gone down the tangent line to negative 0.7, and we can then plug that negative 0.721348 back into Newton's method to get this value. So we've gone up and now fallen down to here, and now then we can just do that again and again, and now we can figure out that the 0 is going to be somewhere near negative 0.876, and it turns out I think that is true to at least a couple of decimal places. It's like 0.00 something. So Newton's method then becomes much more interesting on functions that have multiple zeros, like this very simple quadratic curve x squared minus 4, because it has two zeros, but Newton's method will only converge to a singular zero. And what zero it converges to depends on what value you choose for x of naught. So if we were to have our x of naught be negative 1, we would go like down the tangent line to here, go up, go down to here, and eventually pretty soon we would find ourselves at x equals negative 2. But were we to choose x of naught equals 1, we would go down positive 1, we would go down the tangent line like to here, go up here, down here, and eventually we would end up at x equals 2. And so depending on the value of x of naught, we will get a different value out of Newton's method. And it turns out these areas are called basins of convergence, because they're the places, like basins, where it all will funnel down to one value when run through Newton's method. And so for this one, it's very, very simple. It's a very simple function. If you plug in x of naught less than 0, x of naught less than 0, then you will get the root at x equals negative 2. If you plug in x of naught more than 0, then you will get you'll go down to x equals 2. And if you plug in x equals 0, you won't get anywhere because it's just a horizontal line. This gets even more interesting when we mix it with complex numbers, because Newton's method also works on complex numbers. We can plug in complex values of x of naught, so we could have x of naught equals 2 plus 5i, for instance, or we could try and find complex roots, so we could use Newton's method to get the root of x squared plus 1, for instance, which doesn't have any real roots. Every function, because you can plug in x of naught to be any complex number, it has complex basins, and while our real basins are just a number line. If x is a certain value, you'll get one thing. If x is less than a certain value, you'll get another. But complex basins are areas on a graph, because the complex plane is two-dimensional. You've got your real plane and your imaginary plane, and so this means you get like kind of graphs for complex basins. So with linear and quadratic functions, they're a bit boring, they'll just be rectangles. But if you do that with a polynomial, these basin maps
will become Newton fractals.
What is a fractal? A fractal is essentially a geometric shape that is self-similar across all scales. And what that means is that no matter how much you zoom in or zoom out, it's always going to look the same. You can think of it as a pattern that loops to infinity. If you zoom in on the shape, you're just going to see the same shape over and over again. And the math behind these fractals was discovered in the 17th century by Gottfried Leibniz, but it really didn't take him that far, because all he theorized was an infinite line. If you zoomed in, it was always going to look the same. An actual fractal was never discovered until like about 2 centuries later, with Mandelbrot, who created probably the most famous fractal of all time from the Mandelbrot set. And the name fractal comes from the Latin word fractus, which means shattered or broken, because a shattered window pane or a shattered stone is a great example of a fractal, that when you zoom in, all the branches are just going to keep looking the same over and over again. And another good example of that is this Shrek GIF. No matter how much you zoom in, you keep seeing Shrek over and over again. And wow, that is hard to look at for too long. This is the Mandelbrot set, the fractal of it, which is probably the most famous fractal of all time. And if you zoom in on this, it's always going to look this. You're always going to see the same different shapes over and over again, which is the inherent nature of a fractal. And a specific subset of the fractal is Newton fractals. And these are fractals created by iterating the Newton function and graphing the basins of convergence in the complex plane. So essentially what you do is for every point in the complex plane, you iterate the Newton function for some function starting at that point in the complex plane, and whichever root that it converges to, you color all those the same color. So everything in the green area of this fractal converges to the same root, just as everything in the blue area converges to the same root, and everything in the red area converges to the same root. So you color all the points that converge to the same root, same color, and anything that does not converge, you color black. So you get these shapes that, of course, when you zoom in on them, they are infinitely self-similar. When you graph these Newton fractals, you can get really beautiful images like this, this is all just an example of all these different colors are just basins of convergence of the Newton function in the complex plane.
The Mandelbrot set consists of the complex numbers c, which are generated when the function f sub c of z equals z squared plus c does not diverge when it is iterated from z equals 0. And the Mandelbrot set was originally found by Robert W. Brooks and Peter Metelsky, and they named it after Benoit Mandelbrot. The Mandelbrot set is the most famous fractal and one of the most popular and famous examples of mathematics as an art form. It is widely considered one of the most, if not the most, beautiful mathematical graphs ever created, and its beauty has been seen far beyond simply the mathematics community. One of the most beautiful things about the Mandelbrot set is the length of time and iterations which it takes to repeat the set, and the sheer amount of beautiful patterns and shapes that are generated along the way as you iterate over it. The set is colored based on how close each point is to reaching a specific arbitrary threshold. The black area of the graph are the points where the threshold has not been met yet at this point in the iteration. The next fractal that I'm going to be talking about is the Sierpinski triangle. The Sierpinski triangle is a fractal set that is in the shape of an equilateral triangle. It is one of the most basic fractals in how it scales, as the pattern always looks the same. It is named after
Wacław Sierpiński,
a Polish mathematician who is famous for contributing towards a branch of mathematics called set theory. The Sierpinski triangle is subdivided into 3 equilateral triangles with a hole in the middle. This cycle is repeated, which generates a simple but beautiful pattern that is very easy to picture. Another very interesting aspect of Sierpinski's triangle is that the area of it converges to 0, as the triangles begin to shrink and more gaps form each time it is iterated. The area becomes 3/4 of its previous area after each iteration.
It's common to see mathematics in nature, the Fibonacci sequence in pine cones, the golden ratio in flower petals, but also fractals in the formation of beaches. This is caused by the non-stop ebb and flow of waves, crashing into the sand at a fixed interval that eventually carves the rocks away to create a rough but obvious design. Seasonal storms, for example, contribute significantly to this. On the southwest English coast, there's a stretch of rock formations that share the same self-similar jagged pattern. Using simple pattern analysis, scientists have determined that this coastline was created by repeating a simple process over and over again. This is also seen in the growth of trees and many other flora. Each branch, when examined without leaves, splits off at roughly the same interval from the previous limb all around the tree. While trees aren't infinite, the beginnings of a fractal can be observed in the repeating patterns of the intersections of branches and twigs over the entirety of a tree. The same is true for the structure of many other plants. There's a species of broccoli known as Romanesco broccoli, whose buds form small conic fractals all throughout the head. The repetition of this phenomena gives this vegetable an exotic look, with the conic fractals occurring at roughly the same intervals. Ferns, too, show this behavior, with repeating smaller leaves that continue even up to the apex of the plant. The Barnsley fern takes inspiration from its wild counterpart, and is one of the more simple fractals to be discovered. This fractal resembles the frond of a fern, but each and every leaf consists of the same amount of leaflets, repeating and getting smaller as the fractal goes to a certain point. With math having such a key influence in nature, it is not surprising to see fractals in the plants we see on a daily basis.
You may wonder, what is this weird background noise? So one interesting application of fractals that we saw was the ability for them to be sonified. In this case, what you are hearing right now is a sonification of the Mandelbrot set, where X is mapped to time in the music, Y is mapped to the frequency of the music, and the brightness of the graph is mapped to the volume of the music. All of this creates a very interesting and somewhat alien sounding sound.
We created a program using Java, which is a programming language, and what the program does is it creates a complex plane that goes from -2 to 2 on the real axis and -2i to 2i on the imaginary axis. It's basically the same concept as the xy axis, except it's just one is real numbers and the other is imaginary numbers. And so what the program does is for each point on this plane, it runs Newton's method, which is this is a picture of the function that does that in the program. It runs Newton's method up to 512 times for every single point, and if Newton's method comes within the tolerance value, which is 1 times 10 to the -6, which is like a really small number, if Newton's method comes that close to one of the zeros of the function, then it's determined that Newton's method converges at that point to a certain zero of the function, and then it's colored. The point is colored according to what zero it converges to. So so that's what I said here, is that if it converges, it's colored accordingly. So if it does not converge, then the point is colored black. So you can kind of see that some points here are black, but most of them are colored in. So if it converges to green, that represents one of the zeros that Newton's method converges to. If it's blue, it's another zero, and if it's red, it's another zero. So these two are third degree. It is z cubed minus 1. This is z cubed minus z. So they only have 3 different colors, but the third one is z to the 4th power minus 1. So it actually has 4 colors, so that's why there's a yellow section as well, because that's 4 different zeros. So this is the actual program. You can see if I run the program, then I get this thing from the program, and I can choose which fractal I want to be displayed. So these are the same ones that I showed you here. And so yeah, you can choose which one you want to be displayed. So if I click B, then it's gonna make a new window, and I can look at the fractal. And then it says you can change the view of it. So R is red, G is green, B is blue, Y is yellow, but this one doesn't have any yellow. A is all. So I can change which color I want to see. So if I just click R, then I can see just the parts of the fractal that are red. But and what that means is that it says down here that Newton's method for this function converges to 0, which is just 0 plus 0i. So wherever Newton's method converges to 0, it's red. So that's why this is all the red portion. And then if I change it to blue, then this message is updated. It says that Newton's method is converging to 1 plus 0i, so 1, and that is a different portion of the graph. And I can also do that. I can do that for any one of the functions. So if I run it again and choose C, and then I choose yellow, then I get the yellow portion of the z to the 4th power minus 1 fractal. The only minor inconvenience for this program is the fact that you need to enter in the functions directly into the code, and you also have to enter the zeros of the function directly in the code. Only then the program can actually create the fractal. But yeah, other than that, the program can work for any degree of fractal. You can see if I go to this method about how it colors the fractals, that it can handle like up to like 9 different zeros. So technically a function to the 9th degree. But yeah, that's the program we did.
Fractals are an important and complex part of mathematics. Using Newton's method, we are able to visualize fractals with accurate computer code. But before the term fractal was coined in 1975 by Benoit, there were limited ways to show the truly infinitely many data points created by evaluating a fractal. With increasingly powerful computers, the set was finally able to be visualized, allowing us to see the true beauty of fractals. With the term fractal becoming more widespread, people began to notice the existence of fractals in nature. Scientists discovered many plants with fractal behavior, which means that parts of their structure had self-similar repeating patterns. In this project, we were able to complete a program in Java to create Newton fractals. By applying Newton's method, we could evaluate the fractal by finding what Newton's method converged to, and then draw the data points the program returned. In writing this program, we found that fractals could be created based on fairly simple algorithms, even though they can initially appear to be abstract.
During the project, we made a very important discovery. We have discovered what we believe to be one of the most important equations of all time, and generated a fractal for it. We found the Garrett set, which consists of the equation mushroom hunting plus surfing plus music plus math equals G. We created a fractal for this, which is clearly one of the most beautiful fractals ever created, dwarfing the Mandelbrot set in its beauty.